Okay, so next example 519. Okay, so now we are given a surface sigma, which is the portion of the paraboloid. So we have a paraboloid which is given by z equal to 4 minus x square minus y square, and in this case z always positive. Okay, so if we sketch it, so we have paraboloid, this one. Okay, so this is 4. So when z equal to 0, so we have 4 minus x square minus y square, and right on the xy plane we got a circle with radius 2. Okay, so the surface is part of the paraboloid, which is part of the bow concave down, and C be the circle with radius 2 that forms the boundary of the surface. So where is your closed curve C? So this one. Okay, so that is your this is your C, and this is your surface. So this is information about your surface. Okay, so verify Stokes theorem for the vector field. So if they ask you to verify, meaning that you have to show, so what is the verify mean? You have to show the total or the solution of your left hand side, which is from the look at the Stokes theorem formula. So you have to compute this one where your C is based on the circle with radius 2. You have to obtain this one, and the answer will be the same as in the as given by the surface integral of the curve f dot n ds. Okay. Okay, so let's say here, because in this note they give you the solution. If you look at the solution here, they provide the computation for the left side, which is given by this one, and finally you will obtain 12 pi. So for that, I just leave that for you to redo yourself, just with part of your calculation for the line integral when your C is a closed curve. Okay. And next, if we compute on the right hand side, then you have to deal with the surface integral of the curve f. So in this case, I want to verify, where you have to show the calculation of the left will be the same as the calculation on the right. So in this case, I want to change the instruction which is becomes, so these instructions, and it should be starting from, I just want to change, I forgot to change earlier, so but I don't want to use this, so sorry about that. So just ignore this. Okay, so I change that from here. Okay, I change that from here. Okay, so then it's become, so the instruction then become evaluate the line integral for the over the closed curve C using Stokes theorem. Okay, understand? So let sigma be the portion of the paraboloid z, for which z always positive, and let C be the circle with radius 2 that form the boundary of the sigma in the xy plane. And then from there, evaluate the line integral of the closed curve C using Stokes theorem for the vector field. So, a second. Okay. So then continue here. Okay, so then continue here for the vector field given. This is correct. Okay, so I just want you to change So just put take out the word verify Stokes theorem. I don't want to use that because normally for the exam sake, I'm talking about the exam sake, but it is possible to be asked from the left to the right because we have no much time. If I give you an assignment, it is possible, but for the exam sake, so it will take a longer time if you want to provide the left and the right side. So so now I just changed the instructions. So evaluate the line integral using Stokes theorem for the vector field given, and sigma is always point outward to the surface. So that is the meaning of oriented outward. The sigma, there is a unit normal vector which is always point outward to the surface. So that is the meaning of oriented outward. So based on this new instruction, so since the question here asking for evaluate the line integral, so they ask for it, right, using Stokes theorem. So meaning that you have to show me the calculation using the right side of the Stokes theorem. So in your calculation, you have to show me the calculation about the, okay, so now from Stokes theorem, it is given by, you have surface integral of the curl, not divergent, but curl F dot n ds, where we know that for surface integral we always, so over this over the surface sigma, so for surface integral we always deal with the normal vector. Okay, so here the computation is exactly the same as the surface integral for vector field. Okay, but the difference here, from previous calculation of the surface integral, we only have f dot n ds, right? But now we have grad cross f, so that is a Stokes theorem. Dot, now we have n dA. When we have dA, you should deal with the region. Okay, so all your calculation of the surface integral here is exactly the same as you done in the surface integral for vector field. But the difference here is only, you not only directly use f, but you have to compute the curl f first, and using that new form of vector function, and you have to apply the dot product between the normal vector to the surface. So your surface here is from this equation. Okay, so now we want to, so based on the step to obtain the surface integral for vector field, so we need to find out the normal vector. Okay, after you done that, then you have to compute the curl f, that's the second part, and after that you have to find the dot product between them. So for Stokes, in order for you to compute the surface integral, so your task is becomes more not more complex, but you have extra work need to be done where you have to compute the curl f first. Okay, so now how can we get n? So back to our steps to get the normal vector. So you have to have the equation. Okay, so now to get n, so now we want to obtain the n, so we have to look at our information about the surface that we have. Z is given by 4 minus x squared minus y squared. So we have z is the function of xy. So we know that our region should be on xy plane. Okay, so here your phi in terms of xyz is z minus f xy, where in this case you have z minus 4 plus x squared plus y squared equal to 0. Okay, so hopefully you remember that. So now you have to find the grad phi. Remember? So to obtain the normal vector, you have to first compute the gradient phi. So it's become vector form. So you have to obtain the phi x, phi y, and phi z. Okay, so for phi x, now this is your phi, differentiate with respect to x, so it will give you 2x, and for y it will give you 2y, and z it will give you 1. Okay, so now that is your grade phi. So whether this is your n or you have to make it negative. How can we know that? It should be from your surface. So according to your surface here, since we have the type of equation that we have z is the function of xy. So we only need to focus on which component? I, G, okay. So we have z here. It should be okay. So now look at your surface here. So you want the n should be point outward to the surface. So your surface is bowl concave down. So this is your surface. So when you say that n always point outward to the surface, so meaning that your arrow, so when you choose any point on your surface, your arrow n always point outward. Okay, so they are always point outward. So you can see that the arrow is point to the positive. Okay, right? They are always going up. Okay, where z is always pop. So this one is z pop. Okay, z positive, which means that we have to have the component k must be positive. So if you look at your calculation just now, so now you check your k component here. So it is already positive, right? So we don't need to multiply them by the -1. So it is already positive. So where we can say that this is our n. Okay, n always point outward where k is positive. So that's it. That is the thing that we are looking for, right? So now we accept n is positive gradient phi. So that is our n. So we obtained the n now. So now we want to compute the curl f. So to get the curl f, so now look at the f given. So in the instruction, the f is given by we have 2z, then 3x, then 5y. So find the curl f. So hopefully you remember that you have I, J, K, I. So del x, del y, del z, and del x. I just want to simplify my work. So put all the component. We have 2z, 3x, 5y, and repeat. We have 2z. Okay. So then when you compute, you want to get the component I, so j cross k. So then we got 5 minus 0, right? And then k cross I will give you j component. So you got 2 minus 0, and then I cross j, you have 3 minus 0. So that is your curl f. So now you have to find the dot product. So from the formula here, so you have to find the dot product between the curl f and n. So your curl f just now 5 to 3, 5 to 3, and dot with n you have component 2x, 2y, and 1. So you will get 10x. Don't forget, when you apply the dot product, your answer will be in a scalar form. Okay, so that is a common mistake, so please bear in mind. Okay, so 10x plus 4y plus 3. So that is your, okay, so now I copy this one here. So then your double integral becomes 10x plus 4y plus 3, and you have dA over the region R. Your region is lying on xy plane. So from surface integral here, so it reduced to a general, reduced to a common form of double integral. So this one you have learned previously, right? So then you have to obtain the order of integration, whether dy dx or dx dy. So how can you know that? You have to look at your region. So your region here, where is it? So your region here is on xy plane. So what is the shadow that you can see when you are standing up here? So when you're looking down, you can see this one, right? That is the dominant shape that you can see from the above on xy plane. So you can see the circle with radius 2. So in this case, your region on xy plane is a circle with radius 2. Okay, so since your region is a circular region, so it looks like it's more easier for us to apply the polar in a polar form. Okay, so then R cos theta plus 4 R sin theta plus 3, and then multiplied by R dr d theta. So you have a complete circle 0 to 2 pi, and your R is 0 to 2. Okay, so it looks like you need to simplify your expression here. Don't forget the standalone R here. You have to multiply the R here with all the component inside the bracket. Okay, so then this is how can you integrate. It's not so complicated, but it's a bit long. So the answer will be 12 pi. Okay. Okay. So that is for the example 519 where I modify the instruction. But if you want to proceed with the instruction here, because since I give you all the calculations, so you can also compute the line integral. Okay, you can compute the using the left of the Stokes theorem, which means that if the instruction here if the instruction here I change to, okay, you look at the instruction here, so I change evaluate, okay, instead of evaluate the line integral, so now I change to evaluate the surface integral. So evaluate the surface integral of the curl f dot n ds over the surface sigma using Stokes theorem, meaning that you have to show me on the answer script you are computing the line integral, this one. Okay, so for the line integral, you have to focus on the closed curve. So you can see that the curve which becomes the boundary of the parabola here is a circle. So meaning that you have to find the dr. So you have to get the dr, and the f is given, so you have to find the dr. So in order for you to obtain the dr, you have to find the r. What is r? R is the vector function of the curve. So now your curve is a circle, so find the vector function of the circle. So then that's why in this case we have x equal to 2 cos t, y is equal to 2 sin t. And you can see that this one is located at z equal to 0, and we put z equal to 0. And then you have to find the dx, you have to find the dy, and you have to find the dz, and then multiply with the component f. Okay, and you can see that your t or theta, if you are using t, so your t is angle, so you have a full circle, so your t should be 0 to 2 pi, and you will get this one. Okay, and you can see here the answer is the same as our calculation just now using surface integral. Okay, so that is the example 5.19.